What's going on, you guys, and welcome to the channel. Now in this video we're going to be building a blockchain using the Python programming language, and we're then going to wrap this blockchain inside an API which we will build using FastAPI. Now this video is focused mainly on the blockchain side. However, if you're interested in both or just the FastAPI side or just curious, then hopefully this video is of use to you. However, to begin with, let's go ahead and create the directory. So I'm going to go ahead and call this Rhythmic Blockchain. And by the way, all of this code will be available in the GitHub link that I'll put in the description. So just jump into Rhythmic Blockchain and then create the virtual environment. So Python 3 -m venv. Give that a second. And then let's go ahead and make the necessary installations. So the first one is going to be, better still, let's first activate the environment. So source venv bin activate. And then let's make the installation. So say pip3 install, and then FastAPI, brackets all. And then let's say IPython, and this will just be useful as it's a better Python environment, so we can kind of look at the internals of the blockchain that we create. Just hit enter. This may take some time, so I will come back as soon as this installation is done. Okay, so now that we have everything installed, let's go ahead and open up this directory inside of VS Code or whatever editor you prefer. So I'm just going to do code and then dot. So I have opened up the project inside of VS Code, and the first thing I'm going to create is the blockchain.py file. And before we actually jump into the coding side, let's go ahead and look at what the blockchain is, or what a blockchain is. Now, the first thing is that a blockchain begins with something called a genesis block, or typically known as a genesis block. Now, a block in general consists of some amount of data. It will have like the index, so much like a list element in Python has a index, a block also has an index, which works pretty much the same way. You also have information like the timestamp, the data, or whatever is inside this block, along with some proof, and we'll get to the proof, along with a previous hash. And we'll get to that as well. But for the case of this Genesis block, I don't know why that ran, but let's go ahead and create a mock for it. So as said, it will have an index, which will be an integer value. So the Genesis block will probably start off at 0. It'll have a timestamp, which will just be the current time. So imagine that being that. It will also have the data. So this data we can put whatever. We'll say I am the Genesis block. It will also contain other bits of data, and like I said, it will also have it'll have something called the proof. So proof, and let's just say the proof here is it'll be an integer, and let's say in this case it's 3, and it will also have the previous hash, which is basically some string. So in the case of the Genesis block, we can put this as 0 or whatever, because this previous hash is referring to the block before it, so the hash value of the block before it. As this is the first block, it won't have that, so we'll just put in 0. Okay, so this is a Genesis block. This is what kickstarts the blockchain itself. Now, let's say we want to add another block to this blockchain, and this will hold some data. Let's say it's a message, and it will have something like hello world. So the first thing that we need is we want the hash value of this block. So what we would do is we would throw this kind of dictionary in Python into a function, and we will use this SHA-256 function, but we'll just say hash for now. We'll throw this block in there, so we'll throw all of this into this hash function, and we'll get the value, a hexadecimal value, let's say AAA. This is our value once we've hashed this Genesis block. We then need to use this for our next block. So let's say we have our next block. This will have an index of 1. Timestamp will just say placeholder, current time. We will also have the data. So let's say I am the first block being, actually, let's just say hello world. And the proof, which will be a value, and we'll come back to this, like I said earlier, and the previous hash. And the previous hash is just this value, this 2343 AAA value, this very arbitrary hexadecimal value that we've given for this example. So that's the second block. Let's say we want to add another block to this. This will have an index of 2. The current time, let's say the message is subscribe to Rhythmic. And the proof here will probably be something like this. And the previous hash will be the hash of this block here. So let's say we throw this dictionary object or this block into a hash function. We get some output, which is that. And so the previous hash for this will be this value here. Now, the proof is something that may become a bit more clear later on in the video, but it's the output of some computation that fits some criteria. So we'll have some mathematical computation. The result of that mathematical computation has to match some condition that we will write. And if it fits that condition, then we will get that number. And for this case, let's say it's this huge number here, but that's what it is. Now, in order to hash a block, this will take in some information like the index, the data, the previous hash, etc. And then it will create some hexadecimal value, which is like it's meant to look random. And the great thing about the blockchain is that, let's say someone wanted to change some block in the chain, and let's say they picked the one with index of 1. Now, if they went ahead and changed the data here and said, instead of hello world, they said hello Mars, then this here, this hash output would be completely different. It wouldn't look like 98723FF like that, or without the E. It would probably look something like completely random, like AADDB, something like that. So it'd be like even to a human reader, it would look completely invalid. Therefore, this previous hash would no longer match with that. Hence, or therefore, the blockchain itself is no longer valid. So what may happen is like a group of nodes distributed around will see this and kind of agree on what the actual value is and revert back to the actual state and kind of reject whatever you're trying to do if you're trying to manipulate or mutate the chain itself. So that's a pretty basic overview of how a blockchain works, extremely a basic one. However, there's some very good videos and some articles online that will give you more of a theoretical, in-depth overview of how the blockchain works. But that's enough of the explanation. Let's go ahead and jump into the code. So I'm just going to go ahead and remove this, and let's make the necessary imports for starters. So we need about 3 libraries here. We need the datetime library. We'll import this as _DT. And if you've been following along with my previous videos, then or if you haven't, then I tend to import a lot of my packages or libraries with this underscore, change the name of it and add an underscore. And that's because the PyLint, or if you're using a linter, for example, it will then, let's say you're in another file, you have a new, let's say main.py file, and you're importing blockchain. You don't want to import this datetime from blockchain. That's something you don't want to do. And that's why I kind of prefix it with this underscore, as it will kind of give this protected kind of association with whatever you put the underscore with. So PyLint will warn you if it sees me importing _DT in another file, then it will say you shouldn't be importing this. It has an underscore. It's protected. That's the only reason why. So that's datetime, and let's import hashlib as _hash lib, and also JSON, as we'll need this too. So JSON as underscore JSON. Cool. So let's go ahead and create our blockchain class. We'll say blockchain, and the init, like so. And first of all, the blockchain is technically a list. It's basically a list with some, or a reverse linked list, as it has this previous hash, which refers back to the previous block. So we'll say self.chain equals list, and let's go ahead and create the Genesis block. So the Genesis block, and this will of course be a dictionary which will represent a block. And as kind of like a helper function, let's first go ahead and create a function that will just build our block. So we can say something like create block. And what this will take is some, like a few arguments. So say self, and then we want the data. So whatever information we want to add to our block, this will be a string. We want the proof. We want the previous hash. Let me just shrink that. Previous hash. We want which is a string. We want the index, which is an integer. And that's about it. And all we want to do now is just say that we're going to be returning a dictionary, just for extra typing. And here we can say block equals a dictionary. We'll say that, actually, I hope this size is okay for you guys. Yep. So we'll say index is the index. The timestamp is underscore dt dot time date time dot now, but we want the string representation of that. So let's wrap this inside, or let's kind of cast this to a string, say that. And we need the data, which is just the data that we're passing in. We want the proof and the previous hash. Like so. So pretty standard. And then finally, we can just return block like that. So back in our init, our kind of Python constructor, we can just call it, we can say self.createBlock. Within that, we'll say the data, we'll just manually enter all this. Say I am the Genesis block. We want the proof, we can set that to say 1. We'll say the previous hash is 0. And we will also put in the index, which is 0. Cool. So this is, or 1 actually, and this is important why we want it at 1, but this is our Genesis block. We have that there, and now all we need to do is add this to our chain itself. So we can say self.chain.append, and then Genesis block. So right now it's not doing much. If we were to kind of initialize a blockchain object, it would just add this Genesis block to it. It doesn't really do much more. But let's actually create one of the more important functions, which is the mine block. And we tend to use the word mine here, as it kind of digs its way to the block itself through mathematical computations. We can say self, and then data, which is string, and this will return a dictionary. So the first thing is that we want the previous block. Now, what I want to do is create another helper function, which is get back the previous block. So we can say get previous block. So this will be the latest block in our blockchain. Say self, and this will return a dictionary, so the block. And actually, one thing you could do to maybe improve on this is maybe use like a data class here rather than a dictionary, just so it's a bit more clear. But it's for the sake of this video, I've just kept it as a dictionary. So here we can just say return self.chain and then the last element. So back in our mine block, we can go ahead and first get the previous block. We need the previous block because we also need the proof for it as well. So we can say self.get previous block without the S there. And then we can say previous proof equals the previous block, and then just say proof. And then we can also get the index, so we can say that equals length of self.chain plus 1. That's why the index here is set to 1, otherwise it'd clash. So, or we could just get it from the previous block itself. It's up to you. But the next thing is we want to calculate the proof. Now we'll just say proof equals none for now. And let's create a function that will actually calculate the proof. Now, when it comes to blockchain, there is something called proof of work, and that's pretty much similar to what we're doing now. So for that, let's go ahead and create a function. We'll call this underscore proof of work. This will take in the previous block, or the previous proof, sorry, which is a string. It will take in the index, which is an integer, and it will also take in the data. So data, which is a string. This will just return an integer. And yeah, so let's first go ahead and let's just talk about what proof of work will do. Now, proof of work will start off with a number. It will start off at 1, and then it will go through basically all the numbers from 1 all the way to a certain number, and it will only stop once it's got to a number that meets some requirement, and we will define that requirement. You can define it however you want, but we'll first go ahead and say new proof. So the proof of the current block that we're mining, which is 1, we'll then say check underscore proof equals false, and then we can say while not check proof. So whilst this is false, we can say first to digest. Now this digest is going to be some mathematical operation that we're going to create, and we'll say here, so let's just put none here for now, stop it from complaining. But let's create a function, and this will be to digest. And this is where a mathematical operation will occur. So within that, let's say self, and then a new underscore proof, which is an integer, the previous proof, which is a integer, the index, which is a string, and also the data, which is a string. Now this is going to return bytes. Okay, so let's fill this in. So we'll say to underscore digest equals, and then we're going to wrap this in a string. So we're going to say the new proof, and this is our mathematical like formula. This is what you'll keep secret. You don't want to kind of expose this formula, but we can say something like new proof squared minus the previous proof squared, and we'll just add the index to that. So we can say plus index, and then just add the data to that. So just concatenate to that. So this entire like equation here, you can define it however you want. You don't have to square it. You don't have to. What I would recommend is do something that's a bit complex, that reutilizes different data points, whether it be the new proof, the previous proof, the index, along with your data. It just kind of adds a bit more oomph to your equation. And then finally, we will return the UTF-8 encoded version of the string. In order to do that, you can just say return to digest, encode like that. Now this toDigest, we can go back to our proof of work function. We can call it, we can say to self dot underscore toDigest, the new proof, which is the new proof, the previous proof, which is the previous proof, the index, which is the index, and the data, which is the data, like that. So we've called our toDigest function, which returns back a UTF encoded value of our mathematical operation and concatenated with our data. So now we have this. Now we can apply our hash function to this. So we can hash this value. We can say hash underscore operation, or better still, hash value. And we can say underscore hashlib dot SHA-256, and this will then take in our encoded toDigest, and we want the hexadigest function here. This will just return back a string value of this hexadecimal value here. And what we can do is, this is where our condition comes into play. We can say if the hash value, if the first 4 characters of this hash value is, say, equal to 0, so 4 zeros here, then check proof equals true. And this while loop will no longer run. Otherwise, we just want to increment the new proof by 1. So one thing to note is, if we increase this to more values, so like that, it will take more computational energy to find out this proof. So it'll take way more time. I think it's pretty much exponential. 4 is a good value for the sake of this tutorial. If you want to make it light, you can add like 2, but 4 is fine for now. But just one thing to note, if you want to add more kind of complexity around it, or apply more computational energy, you can add more zeros here. And once this requirement is met, check proof is then true. And then finally, once this while loop is done, once it's met the condition, we can just return the new proof. So yeah, we can actually try this out. We can go ahead and print the proof. So we can say something like new proof. And then let's go ahead and check this out. So let's open up terminal. So I've just added this print statement here just so we can see it. I'm just going to clear all this and just zoom in a bit as well so you guys can see. I'm going to say IPython import blockchain. We'll say BC equals blockchain dot blockchain. We'll say BC, and then we will say the proof of work, which will take in some data. So we'll say hello world. Yeah, it takes an index as well. Not the proof of work, sorry. We want bc.mineBlock. We'll say hello world. And for some reason, it did not print it out, but it executed it nonetheless. I'm not sure if new proof, well, not check proof. Maybe it found it quite, the first one. Just exit. Just try this again. Clear all that. Import blockchain bc dot say bc equals blockchain dot blockchain, and then we can say bc dot mine block, and I'm not sure as to it's because we're actually not calling it. And that was a very silly mistake, so sorry about that. Self dot proof of work will pass in the previous proof, which is the string, which is previous proof, the index, and the data. Now we should get it. We should actually see it. So again, apologies for that. Just oops. Open this up. Let's clear all this. IPython, one more time. Import blockchain bc equals blockchain dot blockchain bc dot mine block. We'll give it some data. Hello world. And then, yeah, so we get to a certain value where it matches. So yeah, we get some value and that's pretty much it. And we're getting new proof as 1. So that's working fine. The next thing we want to do is head back to our mine block. I'm just going to get rid of this proof. I think it might keep annoying us. But our mine block, now we have our proof. We can go ahead and apply that. We can then call our hash. So we want to hash the previous block. We get a hash value for that. We can say the previous hash equals self. And actually, we haven't got to this part yet. So we need another function that will hash a block. So in order to do that, let's create a helper function. We'll call this underscore hash. It will take in a block, so basically a dictionary, and it will return a string. So all this will do is basically, let me just do this here. We'll say hash a block and return the cryptographic hash value of that block. So taking this dictionary, it'll hash it, and it'll give us the cryptographic hash value of that dictionary. Let's say block. Now down below, we can say the encoded block will be underscore JSON.dumps, and we'll throw in the block itself. And sorted keys, we'll set this to true. And we can just encode it like that. And finally, we will call our SHA-256 function. So SHA-256, throw in encoded block dot hexi digest like that. So we get back the string hexadecimal value. So now we can say in the previous hash, we can make use of this new helper function, and we can go ahead and just say self dot underscore hash, and we will say the previous block equals, or block equals previous block. So hash is that block, and then we can go ahead and actually create the block. So we could say block equals self dot create block, and we can just fill all of this in. We can say data equals data, the proof equals the proof, the previous hash equals the previous hash, and lastly we can say index equals index, like so. So now we have our new block. All we need to do now is just append it to the chain. So we can say self.chain.append and then block. And then finally, we can just return said block. So yeah, so let's actually try this out. So let's open up terminal. Let's just clear all this. zoom in. Let me just check to see how you guys see this. I think it's, yeah, maybe it should be fine. But let's do Python. Let's say, let's expand this a bit more. Import blockchain. Say BC equals blockchain dot blockchain. So already we have, for the chain, we have the Genesis one. And what we can do now is say BC dot mine block. We'll pass in hello world. And we get back that block. So we get the hash of the previous one. So see, previous hash is the hash of this object here. So our Genesis block. We have the data, we have the proof, which is this value here, this 92793. We can actually go ahead. I don't know how clear this is for you guys on IPython, but we can say bc.chain. We get the entire blockchain. And let's add another one. So we can say mine block. We'll say this is a cool blockchain tutorial. Run that. We get a new value, this 77529. And how this proof is calculated, remember, is it takes this index, it takes the previous proof, it takes the current proof, or the new proof that is trying out, it takes the data, it runs some calculation, and we check to see if the hash value has 4 zeros at the beginning, then if we get that proof there. So I'm just going to close that, zoom out a little bit. But yeah, so now we can actually mine a block, which is extremely helpful. Let's go ahead and actually create a function that will validate the chain. So we'll check to see if the chain itself is valid, so that no data is kind of out of place. So we'll say is chain valid, and this will just be a self, and all this will return is a Boolean value. So first we'll get the previous block, or the starting, or say current block, which will start off with the first, or the Genesis block, 0, the block index, which is 1, so the index of the first of the Genesis block, and yeah, maybe it might be better to say something like get and then index, like that. And then we'll say while the block index is less than the length of the chain, so self.chain, let's do the following. So we'll say the next block will be the self.chain block index. So that, and then we'll say if the block index, actually it may be better to actually just set this to 1. Let's just do that for now. It may just be clearer, but what we're saying is, so the block index set to 1, while the block index is less than the length of the chain itself, get the next block, which is self.chain block index, so 1, and then so the second one, so it'll start off with the Genesis one, it'll get the next one, and we can check to see if the previous hash of the next block is not equal to the hash of the current block, then obviously something's gone wrong. So we can say block or next block, and we'll say previous hash. If that does not equal the self._hash of the previous block or current block, then we will return false. So if the current block, if the previous hash of that current block does not equal the hash of the block it's actually referring to, then something's wrong. Otherwise, next we will say the previous underscore proof is equal to previous block, or current block proof. We'll call this current proof. And then we can just get the index, the data, the proof, and that will come from block or next block index, the block or next block data, and also the proof. So say next block, like so. So once we have that, we can go ahead and do a hash, like get the hash value. We can say underscore hash lib dot SHA-256. In that, we will say self. We can just call the self dot underscore to digest. And then we'll say the new proof equals proof. We may actually call this next proof. Next underscore indexed, and just for clarity, new proof equals next proof. The next part is the previous proof, so we'll say previous proof equals the previous proof itself. So current proof is the current proof. So previous proof being the current one. Maybe the naming could have been a bit better. I apologize for that. So new proof is the next proof. The previous proof is the current one. The index is the next index. And data equals next data. It's just a formatter now. And then we can just say dot hexidigest, like so. And we can go ahead and run that check again. We can say something like the check we did here to ensure that the first four values of the hash value is the first four characters of the hash value are 0. So we can say if hash value 4, so if the first four are 4, if it's the first four are 0, then, but it's still, if the first four do not equal 4 zeros, then of course we can return false. So I think something's wrong there. And then we can just increment it. So we can say the current block is equal to the next block, and the block index is incremented by 1. And then finally, we can just return true otherwise. So if there are no other issues, return true. Okay, so let's go ahead and try this out again. So let's open up the command line, let's clear all this, just zoom in a bit. Python, we'll say import blockchain bc equals blockchain dot blockchain, and then bc dot mine block, we'll say hello world. We get the first one. Let's add another one. We'll say mine block subscribe to Rhythmic. We've got another one. Now let's go ahead and try out the valid. So is chain valid? We get true. But now let's actually change some information. Let's go into the hello world one, so the one with index 2. So we'll say bc.chain, and then the second element in the list, and we'll say the data is now going to equal hello Mars, like that. So now if we actually look at the chain, we get in our index 2, we get data is hello Mars. The previous hash, nothing else has changed. We've just changed the data here. Now, if we call bc dot is chain valid, we get false. So this hash, the hash that comes from this only works, or this hash here, so the one at index 3, this hash, this previous hash does no longer match this one here, this block here. It only works if hello Mars, if this data is actually hello world. So we can actually change this back to hello world. And now if we actually look at the chain, so we can say bc.chain, we get back to hello world, and we can see if it's valid, we get true. So we're able to now validate our blockchain. So what we're doing is it loops through the actual list. It first checks to see if the next block, if the previous hash of the next block, if it does not equal the hash of the block it's referring to, then return false. It's no longer valid. Then after that, if this checks out fine, then get the current proof, and then hash that. So do the whole operation that we did when we actually created it, check to see if like the conditions are met. So if the first 4 characters of the hash value equals 0, if they don't, return false. Otherwise, all right, check the next block, keep going until you either find one of these conditions not matching. Otherwise, if you don't, then return true at the end. Now that's really it when it comes to actually making the blockchain. So we've gone ahead and looked at how to mine a blockchain. So with the whole computation that we have, let me just zoom out with our 2digest, proof of work, etc. Next, we can actually go ahead and wrap this inside of an API, and we'll build that using FastAPI. So in the beginning of the video, we actually went ahead and installed FastAPI. So what we can do now is just go ahead and create a new file, and we'll call this main.py. Okay, so let me just zoom in a little bit. So this is pretty simple in all honesty compared to what we've been doing. So we can go ahead and create our FastAPI by saying import FastAPI as underscore FastAPI. We also need the blockchain, so we can say import blockchain as underscore blockchain. And let's go ahead and first create our blockchain. So we can say blockchain equals underscore blockchain dot blockchain. And let's create our FastAPI app. So this equals underscore FastAPI dot FastAPI. Cool. So let's first make an endpoint that allows us to mine a block. So we'll just say here endpoint to mine a block. Now this will be a post function, as remember we're passing in data to each of our blocks. To every block that we create, we can say app.post, and we'll say / mine underscore block. And then we'll say this mine underscore block endpoint will take in some data, which is a string. And first of all, we can, before we actually mine anything, let's actually check the validity of our blockchain. So we can say if not blockchain dot is chain valid, then we want to return an error. So we can say something like return underscore FastAPI dot HTTP exception, and we can say the status code is, let's say, 400. And detail, we will just say a message like the blockchain is invalid. Otherwise, we can actually mine the block. So we can say block equals blockchain dot mine block, and the data we just pass in like that, and we can just return the block. Cool, so I'm not going to go ahead and run this just yet. Let's just add a couple more endpoints so we can really check it out. Let's just do another one. We'll say endpoint to return the entire blockchain. So the whole thing, we'll say this is a app.get, so get endpoint, and we'll say blockchain / we'll say def get blockchain, and this will not take in any arguments or any parameters. We'll say if not blockchain dot is chain valid, so we're doing this same old thing. We could probably separate this out into its own separate function, but it's fine for now. We'll say FastAPI, and we'll say the status code. In fact, we could probably just copy all of this for the sake of time. So otherwise, if the chain is valid, we can say blockchain dot chain, and we'll just return the chain. So now let's actually go ahead and try it out. So let's just clear all this. We'll say uv icon main app -- reload, hit enter. The address is already in use. I feel like this port is running somewhere. Let me just close all of these and run the terminal. Just check that everything is running as it should. Okay, so let's just clear all this. UVI corn. So now we have it up and running. Let me just get to my browser and just move this over here. So I'm just going to zoom in a little bit. Say localhost 8000/docs. So let me just zoom in a bit more. Okay, so let's actually get the blockchain. Let's try it out. Let's say try out, execute, and we get back just our Genesis block. I am the Genesis block. Let's go ahead and mine something. Let's say, let's try it out. Let's say, hello, awesome world, execute, and we get back our block. So hello, awesome world with the proof, the previous hash. And this previous hash, remember, is the Genesis block in this case right now that's been hashed. So the dictionary itself, we have the timestamp. And now if we go down here in the blockchain, in this get blockchain, execute it, we have this. So one thing to note is that we're not actually storing our blockchain anywhere. I mean, you could, if you want, dump it inside a JSON file. You could store it in an SQL database, which would obviously be a lot more secure. So like every time we run an instance of this application, like it will start again. So just be cautious that this isn't stored anywhere. But let's just for the sake of completion, let's just add a couple more, like just 2 more endpoints. So we'll add an endpoint to see if the chain or the blockchain is valid, and this we'll say is app.get, and we'll just say validate, and we can add something like is blockchain valid, and all this will do is if not blockchain dot is chain valid, and rather than throwing an error, we can actually just say, to be honest, just say return blockchain is chain valid, like so. So if it is valid, we'll return true, otherwise it will return false. So we can just refresh this here. We go back to validate, we try it out, execute, we get true. Let's actually see what's done there. I'm not sure if it's restarted the entire thing. Execute. Yeah, we just have a Genesis one, so we can add something like cool story, bro. And execute, and we get it. And get blockchain, we have that there, and we can check to see if it's valid. It's still true. So again, like we did with IPython, you know how we created a blockchain and we changed it up. You could do the same here. But as it's not storing it anywhere, I don't know how well that would work. But like I said, you can, if you want, add this to a JSON file to add a bit more kind of flexibility to your app. But yeah, the last one I just want to add is an endpoint that returns the previous block. And this is just a typical get. We say blockchain or previous block. Say previous underscore block. And we can just go ahead and say something like, we just add this anyway, just for an extra layer of security. Otherwise, just say return blockchain dot get previous block. And that's really it. That's really it for this video. I mean, if we go ahead and check out previous block, we should get the Genesis block, which we do. You can add more stuff to it, but I don't want to kind of stretch this video out longer than it already is. But otherwise, if you enjoyed this video, please leave a like and subscribe. I also have a Discord server up and running. However, yeah, it's fairly, I'm trying to stay as active as possible. I really want to grow that. And if you have something to say, please feel free to drop a message there. Other than that, I hope you enjoyed the video and stay healthy, stay safe, and I hope to see you in the next one.